Good morning, everybody. This is Mrs. Audiemeyer. I am going to be going over the first page of the answer key with you for the solutions review. I'm going to work through some of these problems, and if you find yourself having questions, then hopefully this answers them. So if you take a look at the review question number 1, it says, what is the molarity of 245 grams of H2SO4 dissolved in 1 liter of solution? So when I read through this problem and I look at it, I see in the words here, it says, what is the molarity? And I remember that molarity is moles per liter. And I'm not given molarity, so that means that I need to find the moles of my solute being dissolved and the liters of my particular solution. So for me, first thing I want to do is I want to find my moles of the H2SO4. And hopefully at this point you are a champ with this and you need to find your molar mass. So my molar mass, if I add up 2 H's, 1 S, and 4 O's, is 98.08 grams for every 1 mole of H2SO4. Okay, and then when I do the work for that, I end up getting 2.5 moles of H2SO4. Okay, so I've got 0.25 moles of H2SO4, and I'm going to divide them by 1 liter. Now, that math is easy, and it lets me know that my molarity is going to be 2.5 molar H2SO4. Now, this is one way you can solve it. You can find the moles first, and then you can divide by the volume. Another way that we could do this is what we're going to take a look at in number 2. So for number 2, it says, what is the molarity of 5 grams of NaOH in 750 milliliters of solution? So this is kind of a different way that you could show that work. We still want to find molarity, which is going to be moles per liter. So I have the moles per liter that I need to find. I need to find moles, and I need to divide it by the liters. However, it is possible, if it makes more sense for you, to set it up as a ratio in the beginning of 5 grams of NaOH over 750 milliliters of solution. And so in the beginning here, you are putting in the volume right away. Now, we know that we need to convert to moles and to liters, and so we're going to have to do that work. So I'm going to convert to moles of NaOH first, and if I use my periodic table, I find that 1 mole of sodium hydroxide, NaOH, is equal to 40 grams of NaOH. And if you think about units, grams of NaOH will cancel out grams of NaOH, and I'm left with moles of NaOH, which is what I'm going to need to get my final calculation. The 750 milliliters here at the bottom, though, is problematic because in molarity, we have to convert to liters and have our volume in liters. So I'm going to do that work up here, and I'm going to have 1,000 milliliters for every 1 liter, and this allows my milliliters to be canceled out, and now I'm going to have units of moles per liter left when it's all said and done. So I've got my moles here and my liters here. When I put this into my calculator, I want to take 5 divided by 750 times 1 divided by 40 times 1,000. And again, the units I want for my answer are going to be moles over liters. So that's great. When I put that into my calculator, if I do everything correct, my answer should be 0.17 molar NaOH. So you can kind of see with these two problems, 1 and 2, there are 2 approaches to doing this. 1, find your moles first, then divide by the volume in liters. Or 2, you can set up your ratio correct right away, and then convert to moles and convert to liters. So it's kind of a personal preference for you as you go through these. Okay, so how many moles of Na2CO3 are there in 10 liters of 2 molar solution? So I want to get my answer in moles, and I have a volume, and I have a molarity. In my classes, I have always told my students that if I have M times V, you can kind of remember maybe from M1 V1 equals M2 V2. anytime you have M times V, that is going to give you the moles of that particular thing, okay? So if I take a molarity of something and multiply it by a volume, you're going to end up with the moles of that particular solution. So in this case, I like to start off my problems with a number that isn't part of a conversion factor or doesn't have units on top and bottom. So I'm going to start off this problem with 10 liters leading out in the front. I have options with my molarity. I'm going to make a little note kind of over here. Remember that molarity is either 2 moles over 1 liter, or you could flip it and use it as 1 liter over 2 moles. And you just kind of have to decide which one is going to make the most sense for this particular context. So in the case of number 3, I have liters on the top, and I am looking for moles to be as part of my answer. So I'm going to need my mole unit to be up at the top part of this fraction, and the liter needs to be on the bottom to cancel out. And that is where the M times V gives me my moles. Because if I take 2.0 moles of Na2CO3 over 1 liter, this allows liters and liters to cancel out. So if I take volume times molarity, it always gives me my moles. Okay? So my number of moles in this case is going to be 10 times 2, which is going to be 20 moles of Na2CO3. Okay? Hopefully that one isn't too bad. All right, moving on to number 4. It tells me I need to figure out the grams of solute to prepare those particular solutions. So I've still got, if you look at problem 3, I have a volume and a molarity to start with. And in problem number 4A, I have the same thing. I have 0.289 liters of a 0.003 molar copper 2 nitrate solution. So I have the same kind of problem, but in this case, it's not asking me to go to moles, it's asking me to go to grams. So I need to find grams as part of my problem. However, if I am given a volume and a molarity, the easiest thing that I can do is take that to moles, and so that's what I want to do. If I can figure out how many moles of copper nitrate I'm going to need for my solution, I can take my molar mass then and put that into grams using some dimensional analysis. So again, I personally like to start off problems that don't have a fraction in them. So liters is just kind of 1 unit on its own. Molar is moles per liter. So I always start off my problems with just the single unit number there. So I'm going to start off with 0.289 liters of my particular solution, and I am going to multiply it by my molarity. And when I do that, the liters will cancel each other out, and I'm left with moles. So I'm going to take 0.003 moles of CuNO3 per liter. When I do that, liters are gone, and when I multiply these two things together, I get moles of copper nitrate. If it was asking me just to get to moles, I'd stop here. However, I'm not. I'm being asked to do grams. And so what I need to do is I need to figure out what the molar mass of the copper nitrate is going to be. And if you use your periodic table, you get a pretty hefty molar mass of 187.57 grams of copper nitrate for every 1 mole of that. All right, so what I want to put in my calculator then is 0.289 times 0.003 times 187.57 grams of the copper nitrate, and what I get at the end is that I need 0.16 grams of CuNO3 too. Now, just as a quick reminder to you, if I wanted to make this solution in a volumetric flask, what I would do is I would take the weight, this 0.16 grams of copper nitrate, I would weigh it out, and I would put it into a volumetric flask with a tiny amount of water in it. I would swirl it around to get the copper nitrate dissolved, fill the flask about halfway up, swirl it again, fill it up to the line, put the rubber stopper in, flip the flask upside down a couple times to get it all mixed, and then carry on with my day. Okay, so just, I guess, kind of, remember that, keep that in mind. Problem number 4B is kind of the same thing. So I want 16 milliliters of a 5.9 molar lead nitrate solution. And so I'm going to do the same thing. I'm given a volume this time. It's going to be in milliliters. Molarity is moles per liter. So if we think about these numbers, the milliliters and the liters aren't going to work nice together. So I'm going to put the 16 milliliters out first. I'm going to lead with that because it's a number that's not part of a fraction, and I'm going to kind of work with that. So I've got 16 milliliters of my solution, and I need to convert that to liters. So for every 1 liter, there are 1,000 milliliters. Milliliters cancel out, and we keep trucking. My molarity is 5.9 moles of PbNO3 for every liter. Liters can cancel out now. And then to solve for mass, all I need to do is figure out how much the molar mass of lead nitrate is. And lead nitrate is beefy. Lead is super heavy. The molar mass of the lead nitrate is going to be 331.2 grams for the lead nitrate for every 1 mole. When I put this into my calculator, I'm going to multiply by numbers on the top, divide by numbers on the bottom, just like we've done previously. So 16 divided by 1,000 times 5.9 times 331.2. When I put that into my calculator, I get an overall mass of 31.27 grams of the PbNO3 2. Okay, so if I wanted to make that particular solution, I'm going to have to get 31 grams of that. That's a lot of stuff. You say, I only want 16 milliliters of it. However, it's got a high concentration for its molarity, and it has a big molar mass. So it hopefully makes sense to you that you're going to need a little bit more grams-wise of that. Okay. I am not going to go through each of these here, but I am going to go through some of them just to clarify some stuff and then remind you of kind of how to do that, and then you'll be on your own for the rest of these. So when you look at a compound and you want to predict whether it's soluble or not, you need to use the solubility rules and decide what rules apply here and if there are any exceptions to the rules. So if you kind of remember from the solubility rules, and if you forget, there are solubility rules, I believe, printed on the answer key, and you have the list with you. So in the case of, let's say, MgOH, I'm going to be looking for rules for Mg or OH. Now, Mg is an alkaline earth metal. It's not an alkali metal, so there's nothing I can really do about that. But there are rules about the hydroxides. And if you remember with the hydroxides are mostly insoluble. There are 2 notable soluble ones. There is sodium hydroxide and potassium hydroxide. Those are the 2 that are soluble. So in this case, we've got Mg paired with it, which makes Mg insoluble. Remember that insoluble means that that particular thing is not going to dissolve. Okay, I'm going to go down to K2CrO4, potassium chromate. When we look at these 2 things, there maybe aren't rules necessarily for the chromates, but there are rules for things that are alkali metals. Alkali metals are soluble, period. So soluble means that that particular chemical is going to dissolve, and you are going to be able to, if you draw it in a picture, you would draw it as ions instead of a solid sitting at the bottom of the beaker. Okay. Watch out for exceptions with these. A good example would be something like this one here, Hg2Cl2. So if you look at your rules, it says that most chlorides are soluble. However, there are some exceptions to those rules, and it is when your chlorides are with silver, lead, or mercury. And this is mercury and chlorine together. So normally chlorides are going to dissolve. However, when they are with big heavy metals like silver, lead, and mercury, they don't dissolve. So in the case of mercury, mercury chloride here is going to be insoluble. Okay, so follow your rules, and hopefully those are pretty easy. If you have any questions, come to a meet. We'll be there to answer them. We'll be there for the meets Monday, Tuesday, and Wednesday of this week to answer your questions, and then your test is going to be Thursday and Friday. So good luck.